This talk is first about network automation, second machine learning. But before you can actually do automation in a network, you must first start with analytics, because ultimately you want to be able to do what humans do in the network, and you have to basically empower the software with the same know-how that the humans have. And for that, you have to basically collect information from the network. This is telemetry. This has been the subject of many talks. And this includes your topology, routing, IGP, RSVPT, tunnels, BGP, VPNs, the services that run on top of it, as well as the traffic on the network, where the traffic enters the network, where it is exiting. And traditionally, this is done with NetFlow, but you can have segment routing telemetry, push-based telemetry from segment routing. Some vendors have. You can actually have SP counters and lots of things for the traffic. And the performance, that's basically on each of your links, what is the delay, lost, interface errors, and so forth. So this is the telemetry, and then with this telemetry, you must actually understand the data that you collected. You must actually baseline the data. You must find the anomalies, what looks good, what looks basically anomalous, and then from these make conclusions, and then basically provide reports for monitoring or provide services, application services to these network automation applications. And two applications that I'm going to talk about during this talk is one is on traffic engineering, the other one is on path provisioning. But basically, what you collected from the data by itself is not sufficient. You must actually machine learn it, come up with anomalies, baselines, and so forth, and then make use of them in automating the network. The 5 use cases that I have in the slide deck starts from the very simple provisioning of basically assured bandwidth services all the way to on-demand multi-layer traffic engineering. I'm not going to cover use case 4, I have them in the deck, but because that particular use case I covered last year in St. Petersburg. And the only difference in this deck is that this was, back then it was more of a, I promoting that, whereas this time it's actually deployed in a production network. And the key use case is the third one, proactive service restoration. This is the classical definition of self-driving network. Basically, it's a very good use case, and it has a lot of implications to machine learning to actually achieve that. But before I show you any of this automation, why should you automate? This is again a slide from my last year's talk in ENOG in St. Petersburg. I think it is ENOG 13. And this is from a medium-sized service provider. They run a full mesh of RSVPT tunnels, and they have about 20,000 tunnels. And when I look at this network, actually 1,200 of these tunnels are done. I looked at different times. In this particular networks, I don't actually ever see a time where all of these tunnels are up. And if these tunnels are there to achieve traffic engineering and 6% of them down, what does it mean? Does it actually mean that the network is doing fine? Or it has failed to do traffic engineering? But the question that I want to ask you is, if your network has 1,200 tunnels that is down, how long will it take an engineer to examine why they did go down? Why are they down? What is the impact of this? Actually, you log into the router, you do, you show the RSVPT tunnels, the ERO, whatever, you try to find why it failed to optimize, and you go to the next router, you do that, you go to the third router, 1,000, 1,100, and 1,200. That will probably take you a day. And obviously, a lot of people will script this after doing 5 of them or 10 of them. You want to be able to script this and so forth. But this illustrates the need for the automation of the network. Because if the goal here is not really to have TE tunnels, the goal here is to have traffic engineering in the network. And this can be automated. And I'd like to show how it has been automated as well in this talk. But this is the case for the, automating the network, because as the networks grow, traditionally we had the IP MPLS in the backbone of the network. We now have access and aggregation networks, IP MPLS reaching all the way to the edges of the network. Instead of a 1,000-node network, we are now dealing with 20, 30,000-node networks. And for humans to be able to do that is just not possible. Machine learning has been in the news a lot lately, and it has many applications, from autonomous driving to when we talk to our phone and tell them to make sure that I can get to my flight tonight on time, and should I leave, and all of that stuff is actually uses machine learning. The algorithms themselves actually are not new. And they could be very simple algorithms like a simple linear regression all the way to deep neural networks. But even the deep neural networks are not new. Actually, if you look at the Wikipedia, first theoretical paper on this is like more than 100 years ago. But they were very popular in the 80s. However, they were kind of almost like, stagnant and then resurfaced actually in the last, I would say, 5 or 6 years so ago. The problem with that is that the algorithms are not new. We knew how to do neural networks back in the 80s, but we didn't have the same access to the same content we have today. For example, you can ask Siri and show me the pictures of cats in my photos, and it will find you cats, right? And but back in the 80s, I don't think we had thousands of pictures of cats in our phones. But now, on my phone, I probably have 40,000 pictures stored, and lots of cats and dogs and all of that stuff. First, the access to data was not as easy back in the day. As well as these neural networks to actually solve these networks, it requires a lot of computation, and access to computation was also not that available back in the 80s. So basically, even though all of the work has been done in the 80s, only now the technology had caught up, and we can actually, get some of the benefits of this technology. And but it's not as good as what we read in the news makes it sound like. It almost sounds like it can run the network for you. It's not good at doing magic. It has to be trained, and it is actually not that trivial to actually just to operate the network and so forth. So don't expect big in science. We make small steps for a larger step. We don't you have a big leaps on the science. Anyway, it also cannot tell you what it learned. It can show you the pictures of cats, but it doesn't know it's cats actually. And it cannot say this is a cat, or I learned how to differentiate cats or so forth. Also, it's not always accurate, and for example, I have a hard time dealing with Siri because I have an accent, and so forth. It's not like the humans. Humans are also inaccurate, but in the computer, when we usually write an algorithm, we have bugs, but if you forget the bugs, it does exactly what we said, whereas machine learning is not like that. There's always some error in it. For example, there was an accident with a self-driving car in Arizona. A woman was hit. It's not that the car didn't see the person. Car actually did see the person, but the car has to differentiate whether there's an object that it needs to stop for, or it's an object it can drive over, like a trash bag on the road or so forth, and it actually made them wrong decision in this particular case. But what can we do in the networks? I mean, trend detection is, I mentioned that. For example, optical cars may be failing, and then you may actually detect that before it actually fails and take some corrective action. Normal versus abnormal, this is actually a very good application. Clustering, you can actually have lots of customers, and then your customers can have certain behavior, and then you can actually predict that, and then put them into different groups, and then manage them differently and so forth. For example, you can identify your customers who may be willing to leave you for your competition and so forth. And recommender systems, like for example, in the past, if you see this kind of an error on this interface and there is this much data going here, the problem was caused by this particular problem, you can actually learn these. When the same symptoms pop up in the future, you can actually, based on the same symptoms, you can say, okay, this was the issue back then, check these conditions first before actually proceeding. Okay, back to the use cases. The very first use case is the most straightforward one. The service provider said, I want to be able to offer this much bandwidth from this location A to location B. And then can I do that? I said, like, yeah, of course, we can set your RSVP tunnel and then find a good path that can actually do that and so forth. But they did not want the RSVP tunnel. They just wanted to know whether the network can do that or not, right? And they just want to make sure it's not going to cause congestion. And this is actually trivial to solve. You can find the shortest path, no problem. Anybody knows how to do that. You can check the utilization across the, across this path, but you cannot just check the current utilization because this traffic is going to last several weeks and so forth. You need to have an estimate of what's going to happen when they do, different times the network traffic peaks. And also you have to kind of figure out that during this time, some links along this path will fail, and when that happens, what will happen to the traffic? So, I mean, just to ease into the machine learning, basically, if you didn't learn anything, and it's like what most service providers will do today, they will just accept the traffic, right? Because you want to make money, you'll accept the traffic. And then, if your network, if you are running the network at a high utilization, this may actually cause some congestion to this traffic or some other traffic and so forth. And if you just look at the real-time utilization, that's just learn the current time. Basically, you will actually, you'll be okay in the short term because, you'll accept or not accept based on that. But when the traffic peaks, it won't be actually sufficient. And actually, if you learn week-long traffic matrices from the network, you can actually say, okay, with more high accuracy that actually this traffic is not going to cause any congestion on this one. You could actually use neural networks here too, but I'll talk about that in a little bit. The second use case was actually what I thought the first customer asked, but it's basically they want to be able to offer paths in the network which has certain service characteristics. For example, low delay for financial companies or diverse path and so forth. This is actually what people say about the intent-based policies, right? Basically, the intent is I want to be able to provide low delay paths across the network, and you have your subscribers, Cola, Pepsi, Red Bull, and whatever, and they want a path from Los Angeles to New York using this particular service. Oops. And then here are your different services that you configured. There's a template that goes with that. It tells what kind of policy to have, what kind of packet marking it needs to have. All of that basically is done with a template. And then afterwards, you say for Cola, I want a path from LA to New York. This happens to be diverse. It computes and then sets it up using an orchestration system. And interesting use case is this one, actually, the third one, proactive service restoration. In this case, actually, this is about predicting the interface cards will fail. And basically, wide area optics generate heat. The laser have to tune up, heat up, and cool down, and so forth. And as they generate heat, eventually they will die because, it's physics, basically. You generate heat, eventually, you'll degrade, and then eventually it will die. And during this time, the CRC errors keeps increasing. And basically, having lots of CRC errors on a wide area links means this interface is likely to die at some point in the future. And this can actually be learned. And in this particular trial, service provider wanted to proactively reroute the critical services running on this link. Not all the traffic on it, but just the critical services that was running on this link. And we did this, and as I mentioned earlier, basically, interfaces do keep track of the errors on them. You can actually learn this. And then you can baseline this. And based on the baseline, you basically know how much CRC errors is expected and which one is growing and so forth. And then when you detect this, we work with the orchestration system here. You notify the orchestration system that this interface is going to have. An orchestration system says, hey, these are the critical services on them. And I change the intent for this particular, these services and say, exclude this particular link. And then, we compute new paths and then set them up using again, back to the orchestrator. And then that sets up these paths. So in this case, we baseline the CRC error rates. And you have to be a little bit careful here. It's not too hard to do, but you have to be careful because if the interface is not sending any packets, there are no CRC errors. That doesn't mean it will not die. And also, at night, it's sending less traffic, less CRC errors. In the morning, much more. You have to basically normalize it so that you can actually have a normalized baseline that you can actually alert based on that. But this was a very good use case, in my opinion, for neural networks. And how does the neural networks work? On the left-hand side here, there's the image of your retina. And there are these lines on it. These are actually blood vessels. And then there is the neural networks. And the first set of circles on the left are the input layers. If this image is 1,000 by 1,000, there is a million of them. It's not like 3 in the image. There's like a million of them. And there is the hidden layers in the middle, and then there is the output layer. So it's a study by Alphabet. I think it was maybe like 6 months ago. They took these pictures. Actually, they had the archive access to these pictures, and then they were able to estimate, using neural networks, whether the person is going to have a heart attack within the next 5 years. by just an image of your eye. You don't need a doctor for that. It wasn't just that. They were able to estimate the age, whether the person was fat or smoking and had high blood pressure, all of that, just from an image of your eye. It's actually amazing, right? And they were 70% accurate. And the best doctors with using a blood test are 72% accurate. So actually, neural network perform very well. I mean, this is very amazing, you know, especially in the parts of the world where there is no, you know, sufficient doctors for everywhere, right, in Africa and so forth. And the problem here, basically, you have to have, before this network becomes effective, you have to actually train this network. So for that, they had access to 300,000 older images where they knew whether the person had a heart attack in the next 5 years or not. They used that to solve this neural network. And that they had another 14,000 or so images where they said, you know, once we solve this network, is it effective in this 14,000? And they come up with this 70% accuracy. Can we not do that for basically interface failures? On the left-hand side, we have the CRC errors. This is from one of the customers. You have the neural networks. And on the right-hand side, whether the link is going to go down or not going to go down. And this looks very good, except the problem with this is that, okay, we have the algorithm. Solving the neural networks is not a problem. We can do backward propagation, forward propagation, and all of that, solve this. We have the access to the computation, but we don't have the large data sets that these neural networks actually need. For example, in the data set that I use with this particular customers, over a week there was only 48 link failures. In the Alphabet study, they used 300,000 images, and they did say that's not enough, right? I mean, otherwise, if you don't train the network well enough, you know, the car actually drives over the person instead of the trash bag. So you do need to have a lot of them. And basically, for one service provider, being able to train a neural network will actually require data for many tens of years, actually. Anyway, so that's the problem with applying some of the AI techniques into the networking. The key point to take away from this particular use case is that collect data, keep everything. I'll skip this use case. This was in the last year's presentation, but it's also available for you to look at. And then the last use case that I want to cover a little bit is basically multi-layer traffic engineering. In this case, on the top, you have an IP link, which happens to be basically a service path on the transport network underneath. And if you can solve the traffic engineering at the IP MPLS level, it's great. But sometimes under multiple fiber casts, you cannot solve it. What can we do in the case of the, you know, in this case? First, of course, you must collect the optical topology and correlate it to the IP MPLS link. And then when a fiber cut happens, actually, if you had the luxury of re-engineering entire your network in the optical network, you could actually solve this problem. But the question is, basically, what is the good topology in that particular case? And also, each time you rewire the optical network, it causes loss for 5 to 7 minutes in the IP MPLS layer. You need to basically coordinate this. For this service provider, I'll just jump to the example. Basically, this was a lab trial at the service provider. And basically, what we see here, 4 routers on the top, 1, 2, 3, and 4. And inside are the optical switches. One of them is a ROADM, the other ones are not. And then the link on the right fails. And then that IP link between router 3 and router 4 basically fails as a result of that optical failure. And when that happens, basically the traffic from 4 to 3 goes over 2, 1, and 3, and then causes congestion in both of the IP links. But the service provider wants us to do basically rewire the network. Oops, the wrong button. Okay. Do you see it or do I? No. You don't see it. All right. So basically, if you look at the router 4, it has a port that used to go to router 3. That port, after this link has failed, becomes basically available for rewiring. And there is no traffic on it. It can be actually, you know, rewired towards router 3 to router 1 and so forth. Actually, that's what we did. We actually took that port, and there happened to be, the service provider was very generous, there happened to be an available port in the router 2. We actually did a service path to that at the optical layer. From router 2, another service path to router 1. We added them to the basically link aggregation group so that they were available at the IP MPLS layer. And to do that, you have to do multi-layer. At the IP MPLS level, we need to identify the new path and where the congestion is happening. This happens to be a simple network. The congestion happens in both of the links. But in a real network, link may fail here, and the congestion may show up in the other side of Russia, actually, because the traffic now exiting in that direction, and there may be a bottleneck link there. That's the role of the IP layer. And the optical layer, you need to be able to reprovision these. And then the orchestrator coordinates between the two of these layers. Because, IP layer says, I need capacity here, and the optical layer says, I can set up paths, but the orchestrator is the one that takes the input from the IP and then tells the optical layer, go and do this. And the issue that I personally have here, the service provider was generous to make this trial easy for us. They had available ports. In the networks, people don't have interface cards and they're not using it. So what we could actually do in this particular case, if there are lags in the network and some of those lags are underutilized, we can take away some of those links and then use those ports and then add to the, also the failed links, the ports there, and then rewire the optical network. Anyway, the machine learning is actually very promising in networking. Many traffic patterns can be learned. People are also learning traffic matrices with the neural networks, but it needs a lot of data actually to be effective. But even though in the traffic matrices and so forth, we don't have that much data, but there's a lot of data available for DDoS, the traffic anomaly detection, BGP data, and so forth. And I think I'm going to skip this particular use case in the interest of time, since I run out of time. In conclusion, basically, you need analytics. You need to be able to collect this data from the network and then machine learn it and then find trends in this and make predictions about what might be failing and so forth. And then you need automation to reroute the critical traffic around the congestion as well as the equipment that may be failing. And to do the full benefits, you need to have a holistic approach to do both IP as well as the optical layers of the network. Thank you. Jeff.
Why do you call this machine learning? It's just...
Thanks. Any questions, guys?
Yeah, one.
Right. Well, I hear you, but okay, you can go ahead.
Which one of use cases really requires machine learning here?
Actually, all of these cases require machine learning. That you are learning the network's behavior. It does not require neural networks, but neural network is just one algorithm of the machine learning, right? Anomaly detection is machine learning. And for example, the one that we detected, the CR-series were anomalous, that's machine learning.
It looks like vanilla statistical analysis with a few if statements here and there.
So machine learning can be statistical as well as the AI, right? I mean, deep neural networks, I did not use here. But it doesn't mean it's not machine learning. As a matter of fact, when you can have a statistical machine learning approach, you should use that because it's more accurate than the neural networks.
So the real question, so number one, the amount of storage you need to store all this data at some point becomes really prohibitive. I hit this case in my company where we were told the amount of money we need to put into server is more than what we paid you for your solution. So what's your view? How do we deal with it?
So, I mean, there is previous speaker, it was in Russian, but I was able to follow it. There is the data plane, the control plane, and the management plane. This data does not belong in your routers, your infrastructure. This belongs to the management plane. It can be in some data pool someplace in your basically data lake, right? And that's, you don't want to store this inside the network. You want to store it outside. And you must actually, if you want, tomorrow, the network to be self-healing and self-automating and self-running, you must have this data. There is no way around it. And going from a 1,000-node IP network to 100,000 IP access and aggregation network will require you to be able to automate. And you cannot automate it without this data. You don't agree?
I do agree. It's a problem in general.
Okay.
Yes. Okay. Keep looking at both sides. I don't see anybody raising a hand. Oh, you want to say something? No? Okay. Then you take it from me.
just wanted to ask the question. Evgeny Zobnitz of Factor Group. Cengiz, I wanted to ask the question about the machine learning and data out of the network. You said that AI can be used for the traffic matrices, but on our network, the main problem that we have seen right now, we have the traffic matrix out of the net flow, out of the counters of the RSVPT, LDP, or others, but consistency of the data is much worse. Can we use this technique somehow to predict or kind of check the consistency of the data out of the network?
Yeah, I mean, definitely you can use, for example, one data source with respect to the other one to validate they are the same. But in this space, actually the most promising new technology is really the push-based model-driven telemetry. And I know right now it is a single vendor that does this. They have actually for each prefix set, they have a counter. And then with this counter, they are pushing this. It's basically you can get this every 10 seconds, every 5 seconds, and one day maybe every 100 milliseconds. It actually gives you a very accurate traffic matrix. Unfortunately, it's not universal across all the router vendors today. I am only aware of one vendor. Maybe Jeff knows more than one. But this push-based model-driven telemetry is the way to get to traffic matrices.
Question, so you're a vendor, right? You're a consumer of this data in this case.
Yeah, we are, yeah.
How do you normalize? So the amount of data is relatively large.
Yeah,
but
yeah.
how do you correlate IS path to a counter to that data is not really structured, and what do you do on your platform to
I can talk what we do. I don't know whether it's okay, but other people may have better solutions than us, perhaps, maybe even worse, whatever. You know, it doesn't matter, but I can tell you what we do. First of all, we do aggregate. For example, net flow data, right, is by host. We keep that data for a little time for some diagnostics that the person may want to do. We actually aggregate to the routable prefixes, right? Because routing is based on prefixes. And we keep counters for prefixes. And this gives us the sufficient granularity to actually model changes. For example, you can say, hey, instead of peering with Facebook here, if I peer here, how much of the traffic will go that way and how much will continue to go to the existing place, right? For that, you don't need to have, oh, this particular user, this particular, YouTube server, this other, you don't have to have the full matrix. You can actually have a prefix level matrix and you'll be able to do that. That costs a lot.
Okay, thanks. I mean, I'm kind of looking at the timing. I want to make sure that everybody who wants to ask a question does so, because it's good when I have a public dialogue. Cool. And I just want to ask you, any production references you have for this work. I mean, I know that you have probably experienced it inside, but outside the organization. Yeah,
actually, this all 5 use cases is done by service providers
But you just don't name them, right? Because there is no permission, or you don't feel like it's important.
Actually, one of them I have it a permission, and it's actually in the slides. If I can find.
Okay.
It's in Excel. Axiata is a service provider, mobile service operator in Indonesia. And this one is actually in production deployment of this. And I did not go over this use case in this ENOG because I have talked about this 1 year ago in St. Petersburg.
Okay.
And at the time, it wasn't actually in production deployment. It was more of a, but right now it's actually in production, yeah.
Okay, cool, thanks.
Thank you.
I think we'll switch to the next topic. Sorry for
no problem, thank you.
Here.
I appreciate the opportunity.
Yeah.